So on giving heat to any solid, solids expand, right? So this is known as thermal expansion. Why do you think that the solids expand when they are heated? See, the reason would be the thermal heat, or the heat, basically thermal and heat are one and the same thing. The heat when given to a body, it increases the kinetic energy of all the atoms and molecules of which the body is contained of, and then their vibration, their intensity of vibration or motion starts increasing, and that is why the effective interatomic spacing increases, or effective interatomic distance increases between the atoms. So as a whole, the conductors appear to be increased in volume, right? This is what happens. So thermal expansion for solids. So right now what we are talking about, the increase in volume when heat is given to solid, liquid and gas. So right now we have started with solids. In solids, thermal expansion is divided into three parts. One is called linear expansion, another one is area expansion, and third one is volumetric expansion or volume expansion. You can write it volumetric expansion. Now, linear expansion means, suppose there is a rod of length L, okay. Now when you heat it up, the temperature, suppose initial temperature is T or T1, or I can write it like this. Suppose initial length is L1, initial temperature is T1. Now after giving heat or increasing its temperature from T1 to T2, the length got increased from L1 to L2. This much length has increased, okay. So this length is now L2, whereas L1 was up to this much point only. So it has been observed from the experiments that change in length, that is delta L. What is delta L? It is basically change in length, L2 minus L1, right? Change in length is directly proportional to original length, first of all. Why so? See, suppose I have a length of 10 centimeter. I am increasing it by increasing its temperature. How much increase would I get? From 10 centimeter, it might get increased by 1 centimeter, right? So change in length is 1 centimeter, right? Now suppose we have a length of 800 meters or 500 meters. This time, if I increase the length by increasing its temperature, what would be the increase in length? This time the length might get increased by 1 or 2 meters. So compare these two quantities. One side we had a change of just 1 centimeter, and one side we have a change of 2 or 3 meters, that is 200 or 300 centimeters. So that makes sense that change in length will be proportional to original length. How much is the original length? So that what is the scope of increase in length? Second one is change in length is obviously directly proportional to change in temperature, that is delta T. What is delta T now? I'll write delta L is L2 minus L1, delta T change in temperature, that is T2 minus T1, okay. So change in length is directly proportional to these two quantities. Combining these two factors, I'll get delta L, or I'll write it down, delta L is proportional to L delta T. So here I'll put a constant of proportionality to balance the equation, and this time delta L is equal to, the constant of proportionality is alpha L delta T. So alpha, this thing is the constant of proportionality called coefficient of linear expansion. This is called coefficient of linear expansion. So the formula for delta L or this alpha becomes, just note that point that these are proportionality signs and this is an alpha, okay. They don't look like same, but you should know it. Alpha is equal to delta L upon L delta T. Therefore alpha is equal to, or I'm writing it down in terms of L2 L1 T1 T2. Alpha is equal to L2 minus L1 upon L1 delta T is T2 minus T1. This is the formula. I would suggest you not to remember the formula, just remember the main point so that you can derive the formula whenever required, right? Try to do this or absorb this method for as many formulas as you can. Try to derive it then and there whenever required, but don't remember all the formulas, right? Okay, now next is area expansion. So similarly, as we have discussed it in case of length, suppose this was an area, initial area, and initial area be A1, and after change in temperature from T1 to T2, the area got increased by this much amount. This is the increase in area. So let us say final area be A2, initial area was A1. So again, change in area delta A would be proportional to original area and would also be proportional to change in temperature delta T. Combining these two factors, I'll get change in area is proportional to A delta T. Therefore, delta A is equal to, this time constant of proportionality is denoted as beta A delta T. So beta is basically delta A upon A delta T, right? Or in other words, it is A2 minus A1, final area minus initial area upon initial area into change in temperature T2 minus T, right? These are the two main formulas here and this one here. Now third, similarly as we have discussed upon linear and area, this time I have got volumetric expansion where change in volume, we had a sphere of radius r. This time initial temperature again T1 got increased to temperature T2, and this time volume got increased, right? This is the total increase in volume. So from volume increased from V1 to V2, right? Again, following the same method, change in volume is directly proportional to original volume first of all and is proportional to change in temperature. Combine these two factors, I'll get delta V is proportional to V delta T. Therefore, change in volume is equal to, this time the constant of proportionality is gamma. So gamma V delta T. Now we get delta V over V delta T, right? Or in other words, gamma is equal to V2 minus V1 upon V1 original volume times change in temperature, right? They are all similar, but we have a very small relationship between alpha, beta and gamma, okay?